What happens to your idea of far away if 1 second of your time equals 1 light year of distance? That is the rule for this whole trip. 1 second, 1 light year. Before you move anywhere, you need to know what that actually means. A light year is not a year, it is a distance. It is how far light travels in 1 year through vacuum at its usual top speed. When you turn that into a number, it is about 9.46 trillion kilometers. Write it out with zeros and you get a string so long it is basically useless for your brain. So keep the idea, not the full number. 1 light year is trillions of kilometers, not millions, not billions, trillions. Now line that up with something you know. The average distance from Earth to the Sun is about 150 million kilometers. That sounds big, but compared to a light year, it is tiny. You could fit thousands of Earth-Sun gaps end to end inside 1 light year. At your speed, 1 light year per second, you cross the Earth-Sun distance in a tiny fraction of a second. You do not ease out of the solar system, you punch straight through it. So what does that do to the planets that usually feel huge and spread out? Think about your first second of travel. In that 1 second, you move 1 full light year. Pluto orbits the Sun at a distance of a few billion kilometers. That is not even 1,000th of a light year. You do not carefully pass Pluto, you overshoot its orbit many times over in that first second. The neat picture of the solar system we all know, with big gaps between planets, collapses into a tiny region you blow past almost instantly. Now compare your speed to the fastest machine humans have actually launched. Voyager 1, our most distant probe, is leaving the solar system at around 17 kilometers per second. That is already fast enough to circle Earth in minutes. Light does almost 300,000 kilometers per second. You're doing the distance that light covers in a whole year every second. That makes you millions of times faster than Voyager. The probe that needed decades to reach the edge of the Sun's influence would be left so far behind that it basically does not matter for you anymore. Here is the punchline of that first second. You have travelled 1 light year. You have crossed a region that took all of human space travel history to touch, and you still have not hit another star. No collision, no glowing wall of starlight, just more dark. That is your first direct hint that space is not a crowded field of stars, it is mostly empty volume with very rare dots in it. But there is something fake here and you need to be clear about it. In real physics, you do not get to jump to this speed for free. As you approach the speed of light, strange effects kick in. Time for you slows down compared to someone who stays back on Earth. Your energy requirement to go faster grows in a way that becomes ridiculous very fast. You cannot just press the gas pedal and cruise at light speed plus extra. Nature says no. So what are we doing instead? We are switching to a special kind of viewpoint. Think of it like a free camera in a video game. The distances are real, the positions of stars and galaxies are based on real measurements, but the speed of the camera is not bound by the laws that control real rockets or real bodies. We turn off all the limitations about acceleration and fuel and time dilation, and we keep only one rule. 1 second of your clock equals 1 light year of distance along this map. Why do that? Because your brain actually handles seconds on a clock better than trillions of kilometers. When you hear 4 seconds, you feel it in your body. 1, 2, 3, 4. You do not feel 9.46 trillion kilometers. So we convert giant distances into seconds of screen time so you can feel the scale changes directly instead of staring at long numbers. So with that rule locked in, take a simple question. If every second moves you 1 light year, how long until you reach the nearest star? The nearest star system to us is the Alpha Centauri system. It is a small group of stars, and the closest member to us is Proxima Centauri, a dim red dwarf. Its distance is a bit more than 4 light years. That means, at your speed, you're there in just over 4 seconds. You launch from the Sun, count to 4, and you're already passing another star system. Around Proxima Centauri, astronomers have detected at least one planet that matters for our story. Proxima Centauri b. It is a rocky planet, at least a bit more massive than Earth, and it orbits in the region around its star where liquid water could exist on the surface if the conditions are right. We did not spot that planet by taking a clean photo, we inferred it from the way the star behaves. One method looks for tiny wobbles in the star's motion, caused by the gravity of the planet tugging on it as it orbits. Another looks for small dips in the star's brightness when the planet passes in front of it and blocks a bit of light. From those very small changes, measured again and again, we can say, yes, there is a planet there, and we can estimate its mass and its orbit. So when you shoot past that system at 1 light-year per second, you're not passing made-up worlds, you're passing objects we have actually detected and studied, even if we have never been there. Here is the next uncomfortable question. If 4 seconds gets you to the nearest star system, what does far even mean anymore? In everyday life, very basic distances feel large. A few 100 kilometers is a road trip, a few 1,000 kilometers is another country. The distance to the moon already feels absurd. The distance to the sun is something most people never really picture. At your current speed, every one of those distances is rounded down to 0. Earth to Sun, fraction of a second. Sun to Pluto, a tiny slice of your first second. The very idea of far away that you grew up with collapses. Your normal language stops working. City, country, planet, solar system, all of those used to sound big. Now they describe a smaller neighborhood you left behind immediately. Instead, new words are going to take over. Star separation, galactic diameter, cluster distance. You are now living in units of light years and millions of light years, and you are burning through them at 1 per second. This is where the real point of the journey appears. You probably started out thinking the main thing here is you moving fast. But it is not. The main thing is scale. As you keep this impossible speed, you are going to hit bigger and bigger structures, and each one will force you to update your sense of what large means. And by the time you're dealing with galaxies, clusters, and the very early universe, you will be running into the same limits and surprises that force cosmologists to rebuild our picture of the universe from the ground up. So here is the tension going forward. If 4 seconds takes you from the Sun to Proxima Centauri, what happens when you let that clock run for minutes or hours or longer? How fast do you leave home behind, not just visually but gravitationally, historically and physically? If the whole solar system already fits into the first blink of your journey, what does it actually mean to leave home in space? Not just passing Pluto, but crossing the real boundary where the Sun finally stops being in charge. You start with the region we usually call outer space in school diagrams, the Kuiper Belt, a ring of icy objects, Pluto, Eris, and a huge population of smaller bodies. The outer edge of that belt is around 50 times farther from the Sun than Earth is, about 50 astronomical units. Turn that into light years, and it is roughly 8/10,000ths of a light year. At your speed, 1 light year per second, that distance is gone in less than 1,000th of a second. You clear the whole Kuiper Belt faster than the time between 2 frames of a video. Think about what that means. All the famous outer planets, Uranus, Neptune, Pluto, every dwarf planet name you have heard, become tiny flashes in your peripheral vision. You do not thread your way slowly between them. You skim past their orbits so fast that their paths blur into a single faint shell behind you. If you had a distance to counter on the screen, ticking in light years per second, those planetary orbits would barely move the number. So a simple question appears. If crossing the entire planetary zone takes less than a millisecond, was the solar system you grew up picturing ever really big? To find a more serious boundary, you have to go where our actual spacecraft went, Voyager 1. This probe took decades to reach the edge of what we call the heliosphere, the bubble carved into space by the Sun's outflow of charged particles. This edge is the heliopause, and Voyager crossed it at a distance of a bit over 120 astronomical units. That is about 2,000ths of a light year from the Sun. For you, that is a couple of thousandths of a second. One moment you are inside the Sun's particle wind, the next moment you are in the local interstellar medium. This boundary is not a guess. Instruments on Voyager measured changes in the environment as it crossed that region. The density of charged particles around the craft jumped, the pattern of magnetic fields shifted, and the rate at which high-energy cosmic rays hit the detector changed. Those are all signs that the sun's wind has finally lost the fight against the thin gas that fills the space between stars. So when your distance counter slides past that 0.002 of a light-year mark, you're not just inventing a line, you're passing a real border of the sun's influence. But on the scale of the galaxy, you're still extremely close to home. You've only taken a tiny step outside the sun's immediate bubble. If that barely registers, what will it take to actually feel far from the sun? The next layer out is more mysterious, and this is where you spend your first full normal unit of time, whole seconds instead of milliseconds. The Oort Cloud. This is not a neat ring, it is a roughly spherical swarm of icy bodies that are thought to surround the solar system in all directions. The outer edge may extend to about 100,000 astronomical units from the Sun, which is around 1.6 light years. We have not taken a direct picture of the Oort Cloud. We infer it from the behaviour of long-period comets, comets that take thousands of years to complete one orbit around the Sun. When we track their paths back in simulations, their orbits stretch out to enormous distances, far beyond the Kuiper belt. The simplest explanation is that there is a huge, distant reservoir of frozen bodies that occasionally get nudged inward by passing stars or by the overall pull of the galaxy. At your speed, 1 light-year per second, crossing a region that extends out to around 1.5 to 2 light-years from the Sun means you spend about 1 to 2 seconds moving through this halo of potential comets. You're still moving extremely fast, but now at least you can say you spent time in a structure, not just blinked through it. So here is the next question. If you are already more than a light year out, how much control does the Sun still have over you? There is a concept in orbital dynamics called the Hill sphere. It describes the region around a body where its gravity dominates over the pull of a bigger, more distant body. For the Sun, side our part of the galaxy, that Hill sphere extends to roughly a light year or so in radius. That means that out to distances comparable to the outer Oort Cloud, the Sun's gravity still wins over the pull from individual nearby stars. You can put it like this: if you're a small object inside that Hill sphere, the Sun is still your main boss. Another star can pass relatively close, but it will usually just disturb your orbit a bit, not instantly steal you away. The details depend on mass, distance, and speed, but the picture is simple. The Sun is tiny compared to the galaxy, but its gravitational reach is long. Space thins out fast, so even a single star can dominate a huge bubble of volume. Once you finally pass beyond that region, you've done something important. You have left the solar system in a deeper sense than just we passed Pluto. You are now outside the Sun's main gravitational territory. You're no longer in its plasma bubble, you're no longer in its comet reservoir, and you're at the edge of the region where it is the main gravitational player. Now line that up with the next scale. The Milky Way is around 100,000 light-years across. You've just made it out to maybe 1 or 2 light-years from the Sun. On a map of the galaxy, that entire Oort Cloud, this enormous structure that took us decades to even start to understand, would be a tiny dot, a faint fuzz around 1 pixel. So here is the first real perspective flip. You have left home in almost every way that matters. You have crossed the region of planets, passed the edge of the solar wind, moved through the outer comet cloud, and stepped beyond the Sun's strong grip. But compared to the galaxy you live in, you have barely moved at all. You're still basically at the same address, and that raises the next tension. If escaping the entire solar system only moves you a couple of light years out, what happens when you let the clock run long enough to pass dozens, hundreds, or thousands of nearby stars, and start crossing the low-density cavity around us that was blasted open by ancient stellar explosions? What if the space around the Sun isn't calm at all, but the inside of a scar left by explosion? Right now, as you cruise at 1 light-year per second, you're not in a random part of the galaxy, you're inside something with a name, the local bubble. First, the numbers, straight. The local bubble is a cavity of hot, thin gas. roughly 1,000 light years across. From one side to the other, at your speed, you clear it in under 20 minutes. That is nothing for you. But for the galaxy, this region is the result of violent events over the last 10 to 20 million years. X-ray and ultraviolet observations show this space is hotter and less dense than average, and the best explanation is that several massive stars nearby exploded as supernovae one after another, carving out this low-density zone. Here's the strange detail: you think of space as empty, but this emptier region stands out as different from the surrounding gas. Even the empty parts of space have the structure. The local bubble is not a perfect sphere, it is lumpy, stretched, and linked to other cavities, more like overlapping pockets blown in the interstellar medium. You're flying through the after effects of ancient explosions, and your entire solar system just happens to sit inside one of these cavities. If you cross 1,000 light years in about 1,000 seconds, who do you actually pass on the way out? This is where individual stars turn into timestamps on your journey. You already flew past Proxima Centauri at around 4 seconds. Keep the clock running. At about 6 seconds, you hit the distance of Barnard's star, a small, cool red dwarf about 6 light years away. It is faint to human eyes, but in terms of its motion across the sky, it is one of the fastest known. Then, at around 8.5 to 9 seconds, you reach the distance of Sirius, the brightest star in our night sky, part of a binary system about 8.6 light years from the Sun. You keep going. Around 25 seconds in, you reach the distance of Vega, a bright, hot star about 25 light years away, used as a reference point in many observations. On your timeline, these famous stars are just marks on a stopwatch. 6 seconds, Barnard's star. 9 seconds, Sirius. 25 seconds, Vega. The stars that dominate our constellations shrink into simple distance labels, while you chew through light years like steps. So the obvious question is, with stars everywhere on the sky, why are you not crashing into anything? Because even here, space is still almost completely empty. In our part of the galaxy, the average distance between stars is a few light years. That means if you draw a cube of space a few light years on a side, you only get a handful of stars inside it. The Milky Way may contain hundreds of billions of stars, but they are spread out over a disk about 100,000 light years across and a few thousand light years thick. Between those stars, the interstellar medium is extremely thin. On average, there is roughly 1 atom per cubic centimetre, sometimes more, sometimes less, depending on location. That is still real gas, and you can map it using radio waves, especially a specific signal from neutral hydrogen at a standard radio wavelength. When astronomers scan the sky at that wavelength, they build maps of gas clouds, shells and holes, including features of the local bubble. But for you, moving 1 light year every second, that gas is effectively vacuum. Your odds of directly hitting a star by chance are so tiny that for this journey, they round down to 0. If the stars are that far apart, does that mean the galaxy is basically static and calm? Not even close. Look more carefully, and every star is in motion. They all orbit the centre of the Milky Way, and they do not move in a simple flat circle. Some have especially high speeds across the sky, what astronomers call high proper motion. Barnard's star is a classic example. Its apparent position shifts noticeably over just a few years of careful observation. Space missions like Hipparcos and later Gaia have measured the positions and motions of millions and now billions of stars with very high precision, turning the sky from a still image into a measured flow. Some stars are more extreme than that. Runaway stars have been kicked to very high speeds, sometimes hundreds of kilometers per second, after close encounters in dense clusters, or when a companion in a binary system explodes as a supernova and unbalances the orbit. As you race through the local bubble, if you slowed the view and drew arrows showing their motion, you would see long streaks and curved tracks. The galaxy stops being a flat pattern and becomes a swarm of moving points, each one following the combined pull of all the mass around it. So, if you're flying through a giant low-density bubble, with moving stars and thin gas, is this region just a leftover scar? Or is it doing anything right now? This is where the local bubble actually gets more interesting. Recent data suggests that its boundaries are not just quiet shells. The edges of the bubble, where the hot, low-density interior gas pushes against cooler, denser gas outside, line up with regions full of young stars and star-forming clouds. That means the pressure from past supernova explosions has helped squeeze gas along the edges, and that compressed gas is now collapsing under gravity to form new stars and new planetary systems. So the hole you are flying through is part of an ongoing cycle. Massive stars formed long ago, lived short lives, exploded, and carved out this bubble. The blast waves pushed on nearby gas, and some of that gas is now forming the next generation of stars at the bubble's rim. Your own sun may be part of a chain of events like that, and future stars and planets will also form in regions shaped by these old explosions. Here's the real twist. You are not just flying through nothing. You are moving through the visible record of past violence and the setup for future creation at the same time. Space, even when it looks empty, acts like a feedback system, where stars change their surroundings, and those surroundings then control where the next stars will form. And that pushes the tension up again, because if just a few supernovae can dig out 1,000 light-year wide cavity and reshape star formation locally, what happens when you zoom further out and start crossing the entire disk of the Milky Way, with its spiral arms, its layered structure, and its crowded central region wrapped around a supermassive black hole? How do you even process this? You cross an entire galaxy in less time than it takes to watch a short video, while that galaxy took over 10 billion years to build itself. That is what you're doing now. The Milky Way's main stellar disk is about 100,000 to 120,000 light-years across, and at 1 light-year per second, that is roughly a minute and a half of travel time for you from one side to the other. So on your clock, this whole thing's a 90-second dash, but every star you pass had to form in a dense cloud, burn for millions or billions of years, and then, in many cases, explode and recycle its material into the next generation. The spiral pattern you might have seen in pictures is not just artwork. It is mapped using radio telescopes that track cold hydrogen gas, infrared telescopes that see warm dust, and optical servers that count bright young stars. Arms like Perseus, Sagittarius, and our own local Orion spur are traced by real data, not by imagination. If you cross all that in under 2 minutes, what exactly are you crossing? The first idea to fix is that spiral arms are not solid structures. They are not giant fixed bands you could land on. They are more like traffic jams, regions where stars and gas spend a bit more time bunched up compared to other regions. As material orbits the galaxy, it flows into these denser zones, slows slightly, piles up, and then flows out again. The pattern can last longer than any individual star inside it. We see this in how star formation is distributed. In the spiral arms, especially in our Orion neighbourhood, we see more bright, massive young stars. These stars burn hot and blue, and they do not live long. They light up surrounding gas clouds in a particular reddish glow called hydrogen alpha emission, which is basically the signature of ionized hydrogen. When you map that glow across the disk, you see it lining up with the arms. The Milky Way as a whole is turning a few suns worth of gas into new stars every year. And a lot of that action is concentrated along these spiral structures that you're slicing through in seconds. So if the arms are just patterns, not solid structures, does that mean every part of the disk is basically the same, just slightly more or less crowded? Not really. There is a deeper gradient built into the galaxy, and you are flying right along it. Astronomers use the word metals for any element heavier than helium, things like carbon, oxygen, iron, silicon. When we take spectra of stars, splitting their light into colours and measuring the strength of various lines, we can estimate how rich they are in these heavy elements. When you do that across many stars at different distances from the centre, a clear trend shows up, a metallicity gradient. Closer to the galactic centre, stars tend to have more heavy elements. Further out in the disk, stars are poorer in those elements. That makes sense, because heavy elements are made inside stars and in supernova explosions, and then mixed into gas that forms new stars. The inner region is denser and has gone through more cycles of star birth and death, so it has had more time and more material to enrich itself. The outer disk has had fewer cycles, so it is more primitive in its composition. That matters directly for planets. Observations show that stars with higher metal content are statistically more likely to host detectable exoplanets, especially larger ones like hot Jupiters and super-Earths, because heavy elements are what you build solid cores and rocky planets from. So as you rush from the outer disk towards the inner regions, you are moving into a zone where the raw material for complex planetary systems is more abundant. In a few tens of seconds, your path crosses billions of years of chemical evolution. But you might still be picturing this as a simple flat disk, like a thin plate of stars. Is that actually what the Milky Way looks like in detail? The galaxy has vertical structure, and you can think of it as at least two overlapping disks. The thin disk is where the gas, dust, and most young and middle-aged stars lie. It is a few hundred light years thick in the Sun's region, and this is where you find active star formation, open clusters, bright blue stars, and a lot of the spiral arm pattern. Wrapped around and through that is the thick disk, which is puffier, extending thousands of light years above and below the plane. The stars in the thick disk are generally older, with different chemical fingerprints, usually lower in some elements and higher in others, and they move in orbits that are slightly more tilted and more chaotic compared to the thin disk. By counting stars, measuring their motions, and looking at their spectra, astronomers can separate these two populations statistically. At your speed, you move through the thin disk and then up into the thick disk in just a few seconds if you angle your path even slightly. You're crossing layers of the galaxy that formed at different times and under different conditions, but for you, they are just stacked sheets you blow through on your way across. If the galaxy has multiple disks and a chemical gradient, surely at least the overall shape is clean and flat, like those textbook side views, right? Not quite. When we map gas and stars in radio and infrared, we see that the Milky Way's disk is slightly warped and flared, especially in the outer regions. It does not lie in a perfect plane, it bends up on one side and down on the other. The thickness of the disk also increases as you go further out, like the rim of a plate that curls up. This warp is likely caused by gravitational interactions with satellite galaxies such as the Sagittarius dwarf galaxy, and by the pull of dark matter and other asymmetries in the mass distribution. On top of that, you have dust lanes, long dense filaments of dust and gas that cut across the disk and obscure light in many directions. In visible light they show up as dark bands, but in infrared and radio they glow. When you put all this together, the Milky Way is less like a perfect flat vinyl record and more like a slightly bent, twisted and dusty structure, nudged and pulled by everything it has eaten or passed near over billions of years. For you, racing across it in about 90 seconds, all of those details compress into a blur. You enter the outer disk, cross spiral arms traced by hydrogen and young stars, dive through the thin disk, skim the thick disk, move into regions with higher heavy element content, and ride over subtle warps and flares without even having time to react. But underneath that blur is a history, mergers with smaller galaxies, repeated star formation, chemical enrichment, and slow distortion by gravity. And that brings you to a sharper question. If the quiet outer disk is already this complex and dynamic, what happens when you aim straight for the center, where stars are packed much closer together, where orbits are faster and more chaotic, and where a supermassive black hole, millions of times the mass of the Sun, is sitting and quietly bending space-time itself? What happens when you point your impossible 1 light year per second straight at the most dangerous object in the whole galaxy and just keep going? Not toward a random star, but toward the place where gravity stops being a gentle background and starts running the show, the galactic center. As you head inward from the disk, the sky around you stops looking like a scattered field of stars and starts to thicken. Star counts go up. The light gets more crowded. But our normal view from Earth is blocked by dust, so if you want to see what's really there, you have to switch to infrared vision. When astronomers did that, they found something shocking: stars very close to the centre, moving at thousands of kilometres per second on tight, fast orbits around a point that looks dark. One of those stars is called S2. It loops around the centre in about 16 years, on a very stretched out elliptical path. By tracking its position and speed again and again over decades, we can use basic gravity to work backward and ask, how massive does the central object have to be to keep this star in orbit? The answer is roughly 4 million times the mass of the Sun, packed into a region smaller than our solar system. That is how we know there is a supermassive black hole there, called Sagittarius A. You never see the black hole itself, you see what its gravity forces the stars around it to do. So here's the question: what does space look like when you pack that much mass into the middle of a galaxy? Near the centre, the star density goes through the roof. Instead of a few stars over a volume several light years across, you can have millions of stars within a region just a few light years wide. Imagine shrinking the distance between average neighbours from a few light years to a fraction of that. Again, you don't see this clearly in visible light because dust blocks it, but infrared telescopes cut through the dust and show a crowded, messy, bright environment. The orbits here are not slow, lazy paths like the Sun's 200 million year trip around the galaxy. Around Sagittarius. A star. Some stars complete an orbit in a few decades, some in just a few years. They race along curved tracks, constantly changing direction because of the black hole's pull. If you could slow your journey down and watch them, you'd see them swing in close, whip around, then shoot back out, classic gravity slingshot behaviour. But at speeds and distances that make the solar system look tame. But a black hole is not just about stars, it is also about what happens to gas that gets too close. Right now, Sagittarius A is relatively quiet. It is not swallowing matter at a high rate, but it is not completely silent either. Every so often, instruments pick up flares in X-rays and infrared light coming from very near the event horizon, the no-return boundary. These flares are probably blobs of gas that fall inward, heat up to extreme temperatures as they spiral close to the black hole, and then radiate energy before they disappear. So we can see stars whipping around something invisible, and we can see gas flaring as it brushes the edge. Is that enough, or do we have a direct picture of the black hole itself? A few years ago, a global network of radio telescopes linked together into one Earth-sized instrument called the Event Horizon Telescope did exactly that. They observed Sagittarius A at a specific radio wavelength and combined the data. The result was an image showing a bright ring of emission with a darker patch in the middle, a shadow, where the black hole bends light so strongly that fewer photons reach us from that region. It is not a sharp, simple photograph like a phone picture, but it is exactly what general relativity predicts for light around a black hole of that mass. For the first time, we had direct visual scale evidence that this thing is real and behaves the way our best gravity theory says it should. But the galactic centre is not only about what is happening today, it also carries signs of a more violent past. Above and below the plane of the galaxy, stretching tens of thousands of light years out, there are two giant lobes of gamma-ray emission, discovered with a space telescope that studies high-energy photons. These are called the Fermi bubbles. They sit like two huge, faint hourglass shapes sticking out of the galaxy's core. What could make structures that large? The most likely explanation is that in the past, the region around Sagittarius A went through an active phase. Either rapid feeding of the black hole, or strong bursts of star formation and supernovae near the centre, drove outflows of energetic particles and gas along the poles of the galaxy. Those outflows injected energy into the surrounding halo and left behind these bubbles. In other words, our quiet-looking Milky Way probably had a stage where its core behaved like a small quasar, bright and aggressive on cosmic terms. So the centre of the Milky Way is crowded, fast, and shaped by a black hole that we did not even know about a century ago. Does that mean our galaxy is a special case? That's the really important twist. When astronomers started measuring the motions of stars in the central bulges of many galaxies and estimating the masses of the black holes in those centers, they found a pattern. There is a strong correlation between the mass of the central black hole and the mass and motion of the stars in the surrounding bulge. Bigger bulge, bigger black hole, smaller bulge, smaller black hole. It is not a perfect single line, but the trend is tight enough that it is hard to dismiss. That tells you something deep. Supermassive black holes are not random mistakes that happen now and then. They are tied into how galaxies form and grow. As gas falls into galaxies, forms stars, and sometimes feeds the central black hole, energy gets pushed back out into the surrounding gas. That feedback can heat, stir, or even blow gas away, which controls how fast the galaxy can keep making new stars. The black hole and the galaxy evolve together. You cannot tell the full story of one without the other. For you, racing through at 1 light year per second, the whole central region is just a few hundred light years of especially bright, messy real estate that you cross in a few minutes. You see crowded star fields, strong gravity, flares near the event horizon, and you punch through the faint gamma-ray bubbles left by ancient outbursts. But behind that short crossing is a much bigger point. The idea that galaxy centers and their black holes are part of the basic design of cosmic structure, not optional extras. And now there's a new tension building. You've gone from the quiet outer disk to the dense central region locked to a supermassive black hole. So what happens when you stop hugging the plane of the galaxy and head up, out of the disk entirely, into the halo, where the bright stars thin out, old star clusters orbit like ancient satellites, and most of the mass around you suddenly stops showing up in light at all? What happens when you stop skimming along the bright starry plane of the galaxy and just punch straight up out of the disk into the dark? At 1 light year per second, you leave the Milky Way's main glow fast. The star fields thin out, the dense clouds and bright nebulae drop away, and the sky starts to look more like a sparse shell than a flat band. But it doesn't go completely empty. As you climb out of the plane, you start seeing something different. Tight, concentrated balls of stars hanging in the halo. These are globular clusters. Each one can hold hundreds of thousands, sometimes up to 1 million stars squeezed into a region only a few dozen light years across. They don't sit in the disk like open clusters. They orbit around the galaxy and the halo, on long, tilted paths. We've catalogued over 150 of these clusters in the Milky Way. When we take spectra of their stars and count their types, we get ages over 10 billion years. That means these things formed early, when the galaxy was young and still assembling. They are like fossil records, frozen snapshots of what star formation looked like in the first stages of the Milky Way's life. As you cut through the halo, you're seeing not just distance but time, because those clusters remember a version of the galaxy that does not exist anymore. So here's the next question. If the outer halo is full of these old star swarms, what do the motions of everything out here tell you about what the galaxy is really made of? This is where the visible stars stop being enough to explain what's going on. If you take the Milky Way, look at how fast stars and gas orbit at different distances from the centre, and you only count the gravity of the stuff you can see, you'd expect a certain pattern. Inside, where most of the mass is, speeds can be high. Further out, where there are fewer stars and less gas, the orbital speed should drop like the outer planets moving slower than the inner ones. That is not what we measure. When astronomers map the rotation curve of the galaxy, plotting orbital speed versus distance from the centre, the curve doesn't fall off the way visible matter predicts. It stays flat. Stars far out in the disk and in the halo orbit faster than they should, if all the mass were in the luminous part. The same thing shows up when you look at how globular clusters move and how gas clouds behave. This mismatch is not a minor detail. It is a big, hard problem. Something is adding extra gravity without adding light. That something is what we call dark matter. We don't mean mysterious vibes, we mean there is actual mass there that barely interacts with normal matter except through gravity, and it refuses to show up in telescopes. So if most of the gravity comes from something you cannot see, what are you really moving through right now? The best models we have say the Milky Way sits inside a dark matter halo, a roughly spherical distribution that extends far beyond the visible disk. That halo probably reaches out to 200,000, maybe 300,000 light years from the center, much larger than the bright part of the galaxy. When you add up its mass, it comes out to something like 5 to 10 times the mass of all the stars, gas and dust combined. So as you rush out through the halo, almost everything controlling your motion is invisible. The stars and clusters you do see are like tracer particles in a fluid, showing you where the gravitational field is strong. But they are not responsible for most of that field. You are flying through a region where the majority of the mass doesn't shine, doesn't absorb light, doesn't emit light, but still sculpts orbits, bends paths, and holds the galaxy together. That raises a sharp question. If we can't see dark matter directly, how do we map its shape and test that picture? One powerful way is to watch what happens to smaller galaxies and clusters that get too close to the Milky Way. Gravity pulls them in, stretches them, and over time tears them apart. The stars from those shredded systems don't just vanish, they spread out along their orbital paths, forming long, thin structures called stellar streams. Space missions like Gaia have made this visible in detail. When you plot star positions and motions precisely, you see long arcs and rivers of stars across the sky, moving together in coherent patterns. Each stream is the remnant of some past meal, a dwarf galaxy or a globular cluster that got disrupted by the Milky Way's gravity. The shape and thickness of these streams and how they curve are sensitive to the underlying gravitational field, including the dark matter halo. By studying them, astronomers can infer how the invisible mass is distributed. So as you cross the halo at 1 light year per second, you are literally flying through the debris of galaxies the Milky Way has eaten, and those debris trails are giving away the shape of the hidden halo around you. Now comes the big reveal. Without that dark matter halo, the numbers just do not work. The outer parts of the galaxy would not have enough gravity to keep stars bound. Their speeds would fling them off into intergalactic space. The flat rotation curve would make no sense. The pattern of streams and clusters would not match what we see. It was exactly this kind of problem, first seen in galaxy clusters and then in individual galaxies, that led to the conclusion that only a small fraction of the universe's matter is normal stuff. The rest, roughly 27% of the total energy budget of the universe, is dark matter. And the part you're in right now, the galactic halo, is where that invisible component dominates. The majority of the matter around you does not emit light, does not absorb light, does not collide like gas, but it shapes everything. It controls how galaxies rotate, how they merge, how they grow, and how structures formed over billions of years. So you've gone from the bright disk, where stars and gas run the show visually, to a region where light is just a thin decoration on top of a much larger, invisible mass. You're finally seeing the universe the way gravity sees it, not the way your eyes do. Which sets up the next step. If your own galaxy is just one dark matter halo among many, orbiting and interacting with others, what happens when you keep going, leave the Milky Way's halo itself, and head out into the larger family it belongs to, the local group, where another giant galaxy, Andromeda, is already falling toward us for a future collision? How do you feel about the fact that our entire galaxy is already moving toward a head-on collision and nobody asked you first? As you leave the Milky Way's dark matter halo and keep that 1 light year per second speed, the next big structure on your path is not empty space, it's another full-size galaxy, Andromeda. On your timer, the distance is simple. About 2.5 million light years means about 2.5 million seconds. That's under an hour in this absurd timescale. In reality, that distance is measured very carefully. Astronomers use standard candles, special kinds of stars whose real brightness we understand, like Cepheid variables and certain types of red giant stars. By comparing how bright they should be with how bright they look, we can work out how far away Andromeda is. The answer comes out to around 2.5 million light-years, and the error bars are small. Andromeda is not just sitting there either. When we measure its spectrum, we see that its light is slightly shifted toward the blue, meaning it is moving towards us, not away. Combine that with proper motion measurements, and you get a relative approach speed of around 110 kilometers per second. That is slow compared to your 1 light-year per second cheat mode, but it is very fast on galactic terms. The simple conclusion: the Milky Way and Andromeda are on a collision course. So here's the uncomfortable question. What does collision even mean when you're talking about two huge, mostly empty galaxies? As you get close, Andromeda resolves into a massive spiral larger than the Milky Way, with a bright central bulge, long arms, and its own swarm of globular clusters and satellite galaxies. You're not just visiting a neighbour, you're meeting another full gravitational system with its own dark matter halo. The two halos are already interacting, tugging on each other gently. Over billions of years, that pull will grow, and the galaxies will start to fall together. But the local group is not just a two-galaxy show. If you zoom out a bit more, another major member appears, the Triangulum galaxy, also called M33. It's a smaller spiral likely orbiting within the same broader structure, possibly even interacting with Andromeda. Around these main spirals there is a cloud of dwarf galaxies, more than 50 that we have catalogued so far. Some are fairly bright, like the large and small Magellanic Clouds near the Milky Way. Others are ultra-faint dwarfs, tiny systems with very few stars and a lot of dark matter. Deep surveys, especially wide-field imaging from modern telescopes, keep finding more of these faint satellites, little smudges of light that turn out to be entire galaxies with only a few 100,000 stars. They are so dominated by dark matter that the stars are just tracers, tiny hints of a much bigger invisible mass. As you fly through the local group, you are not in empty space between two neat islands, you are in a small swarm of galaxies from giants down to barely their dwarfs. So if everything in this region is orbiting everything else, what does the future actually look like? Do these galaxies just drift, or do they crash? This is where simulations step in. You can't watch a real galactic merger in real time. It takes billions of years. But you can feed the current positions, velocities and masses of the Milky Way, Andromeda and the local group into an M-body simulation, a big calculation where gravity acts on every chunk of mass. Run that forward in time and you see a clear result. In roughly 4 to 5 billion years, the Milky Way and Andromeda will make their first close pass. Their disks will distort, long tidal tails will stretch out, and over several passes they will lose orbital energy and finally merge into a single larger galaxy. Here's the key point. A collision of galaxies is not like two solid objects smashing. The stars are far too spread out for lots of direct star-star impacts. The real action is in the gravitational fields and the gas. The dark matter halos pass through each other and settle into a new combined halo. The gas clouds in the disks compress, slam into each other, and trigger bursts of new star formation. Orbits are shuffled, some stars get flung out into long streams, others sink toward the new central region. After a long chaotic phase, simulations suggest the end product will likely be a giant elliptical-type galaxy, sometimes nicknamed Milkdromeda or something equally cursed, but the important bit is the shape: rounder, more random orbits, less crisp spiral structure. As you watch this in fast forward in your mind, rolling billions of years into a few seconds, you're seeing the local group's future locked in by gravity right now. So what does the local group show you about galaxy types just from this small sample? Even in this tiny patch of the universe, you already have a catalogue of designs. The Milky Way and Andromeda are large spirals with disks, bulges and spiral arms. Triangulum is a smaller spiral. The Magellanic Clouds are irregular dwarfs, with lopsided shapes and bursty star formation. Other dwarfs are spheroidal, roughly round balls of old stars with very little gas left. Their shapes and contents tell their stories. Spirals usually have enough cold gas to keep forming stars, and their disks remember ordered rotation. Irregulars are easily disturbed by interactions and often show signatures of recent encounters or gas inflow. Dwarf spheroidals tend to have lost their gas, maybe stripped away by bigger galaxies or blown out by supernovae, and now just drift as dim old star clouds. These are not guesses. High-resolution imaging from space and ground telescopes combined with spectra show the motions of stars, the presence or absence of gas, and the ages of stellar populations. When you line those up, you can match morphology, the shape of the galaxy, with its history, how much it has interacted, how violent its environment has been, and how much fuel for star formation it still has. So if even a small neighborhood like the local group is full of interactions and future mergers, is any galaxy really alone? That's the big realization this region forced. The Milky Way, Andromeda, Triangular, and all their dwarfs are gravitationally bound to each other. They orbit within a shared dark matter potential well, and over time they will merge, strip, and rearrange each other. When astronomers looked beyond, they saw that this is not unusual. Galaxies generally come in groups. Those groups join larger clusters. Clusters sit within even larger structures called superclusters, all threaded together along the cosmic web. The local group is just one such family, probably spanning 10 million light-years or so, living inside a bigger structure dominated by the Virgo Cluster, and then by our home supercluster region. You're not flying from one isolated galaxy to another in a void. You're moving through a hierarchy, where each level sits inside a larger one, like nested gravitational wells stacked across tens, then hundreds of millions of light-years. So now the tension ramps up again. You've gone from a single galaxy and its hidden halo to a small swarm of galaxies that are already locked into a future merger. The next step is obvious and uncomfortable. If a small structure like the local group already contains multiple massive galaxies and dozens of satellites, what happens when you keep going, push your 1 light-year per second speed out to tens of millions of light-years, and fall into a full galaxy cluster like Virgo, where thousands of galaxies, huge pools of hot gas, and even stronger dark matter clumps all fight for control? What happens to your sense of danger when you realize the thing pulling on you is not one galaxy, but thousands of them locked together in a single gravity well? As you leave the local group behind and keep that 1 light-year per second speed, you're not just drifting into random deep space, you are falling toward the nearest rich galaxy cluster, Virgo. Now, your distance counter is counting in tens of millions of light-years. The Virgo cluster sits at around 54 million light-years away. That number is not a guess. It comes from 2 lines of evidence. First, redshift, how much the light from those galaxies is stretched by the expansion of the universe. Second, standard candles, objects like Type-A supernovae, and certain well-understood stars whose true brightness we know. By comparing how bright they should be to how bright they look, we can calculate distance. Those methods together say, yes, Virgo is tens of millions of light-years out, and yes, it is a major mass concentration in our larger neighborhood. So now ask yourself, if the local group was already a decent-sized family of galaxies, what does it mean to fall into a full cluster where gravity is turned up much higher? As you approach Virgo, individual galaxies stop being rare landmarks and start showing up in crowds. The cluster contains thousands of galaxies, big spirals, giant ellipticals, and many dwarfs, all bound together. They are not sitting quietly, they are moving at high speeds within the cluster, hundreds to over 1,000 kilometers per second in random directions. When astronomers measure these velocities, they can work out how deep the cluster's gravitational well must be to keep all those galaxies bound instead of flying apart. Here is the punchline. If you only add up the mass from the stars you see and the gas you can detect directly, there is not enough gravity. The galaxies are moving too fast. Just like with individual galaxies and their flat rotation curves, you hit the same problem at a bigger scale. Something invisible is adding extra mass. Dark matter shows up again, this time as the dominant component of the cluster's mass budget. But the space between those galaxies is not empty, and this is where clusters get even more intense. The region between cluster galaxies is filled with gas so hot it does not glow in visible light at all. It glows in X-rays. We are talking tens of millions of degrees. X-ray observatories like Chandra and others map this intra-cluster gas. When you look at their data for Virgo and for other big clusters, you see huge, smooth clouds of X-ray emission filling the cluster volume, not just sitting in individual galaxies. From that emission, you can estimate how much gas there is, because the brightness and spectrum depend on how dense and how hot the gas is. The result, the total mass of this hot plasma is greater than the combined mass of all the stars in all the cluster's galaxies. So even at the cluster scale, stars are not the main normal matter component the hot gas is. And then, on top of that, you still need even more mass, dark matter, to explain the motions and hold the whole structure together. Clusters are basically dark matter wells with gas and galaxies stuck inside. So now the question gets sharper. If you can't see most of the mass, how do you prove it is really there and not just a math trick? This is where gravitational lensing gives you a direct, brutal test. According to general relativity, mass warps space-time, and light follows curved paths in that warped geometry. If you have a very massive cluster in front of more distant galaxies, the light from those background galaxies gets bent. On the sky, they can appear stretched, magnified, or even as multiple images and long arcs. In clusters like Bell 1689 and others, we see exactly that, dramatic arcs and distorted shapes of background galaxies wrapped around the cluster core. By measuring where those arcs are and how strong the distortions are, you can work backward to map the mass distribution of the lensing cluster, like reading a fingerprint. When you do that, again, the inferred mass is far more than you can explain with stars and hot gas alone. The missing mass matches what you also infer from galaxy speeds and gas temperatures. So now you have two completely different methods, dynamics and lensing, both pointing to the same conclusion. A massive extended dark matter halo holding the cluster together. At this point you've seen dark matter in several different guises, in the flat rotation of galaxies, in the motion of halo stars and the globular clusters, in the streams torn from dwarf galaxies, and now in the extreme environment of a galaxy cluster. It keeps showing up in the data, different methods, different instruments, same basic story, most of the mass is invisible. So what did Virgo and other rich clusters really do to our picture of the universe? They made it obvious that galaxies are not the final units of structure. Before this kind of work, you could imagine the universe as mostly made of isolated galaxies flying through space. Clusters killed that idea. They showed that galaxies themselves live inside larger bound systems, with their own dark matter halos, hot gas and complex dynamics. And then, as surveys pushed further, we saw that those clusters are grouped into even larger patterns, superclusters, and that those superclusters are arranged along filaments and sheets with huge voids in between. Every time you zoomed out, you found another layer, and in every layer the same mass discrepancy pushed you back to the same answer. Most matter is dark. The luminous parts, the pretty pieces, the bits we see with eyes and cameras are the minority. The universe is hierarchical, and the more layers you add, the more clear it becomes that gravity is being controlled by something we still do not understand at the particle level. For you, falling into Virgo at 1 light-year per second, all of this is compressed into a short, intense crossing. You see thousands of galaxies flying in a deep potential well, a fog of X-ray bright gas, strong lensing arcs cutting up the background, and a mass map that refuses to match the light map. You are watching gravity expose a hidden skeleton underneath everything. And that leads to the next step up in tension, because if even a massive cluster like Virgo is just one node in a much larger flow of galaxies, what happens when you zoom out again to hundreds of millions of light years and start following how whole regions of the universe are moving, not just where they are, tracing out superclusters like Laniakea and the giant attractions that are pulling entire swathes of galaxies through space? What if where you live isn't a point in space at all, but a direction you're slowly sliding in, along with tens of thousands of galaxies? You've left the local group, you've fallen through the Virgo cluster, and at 1 light-year per second, you're now moving across hundreds of millions of light years. This is where your address stops being a galaxy and starts being a flow. The structure you're in has a name, Laniakea, our home supercluster. It's not a neat walled-off island, it's a region about 500 million light-years across, defined in a specific way. Astronomers didn't just draw a circle around a bunch of galaxies and say, that's a supercluster. They looked at how galaxies move. They mapped thousands of them, measured their redshifts to get the general expansion, then used distance indicators to figure out how far they really are. Subtract the smooth expansion, and what's left is the peculiar velocity, the motion caused by local gravity. When you do that across the sky, you see a pattern, flows of galaxies drifting toward a region we call the Great Attractor. All those streaming motions together outline Laniakea. So here's the weird part. The cosmic expansion is pushing everything apart, but gravity from dense regions is tugging things together at the same time. Which one decides your path? Every galaxy in this region participates in both. On the large scale, space itself is expanding, and if gravity didn't add extra structure, everything would just follow that smooth Hubble flow. Redshift increasing with distance, no extra wiggles. But when you add real lumpy matter, overdense regions pull harder. Galaxies start to fall slightly toward these masses, gaining peculiar velocities on top of the general expansion. To measure those peculiar velocities, you need both the galaxy's redshift and an independent distance estimate. One common tool is the Tully-Fisher relation for spiral galaxies, which links how fast a galaxy rotates to how bright it really is. Compare that true brightness to how faint it looks, and you get distance. Combine that with redshift, and you can see whether it's moving faster or slower than pure expansion would predict. Do that for many galaxies, and a picture appears. They're not just sprinkled randomly, they're flowing. Long arrows point towards certain regions, like water draining into basins. Those basins are where the mass is. So what exactly are you falling toward? What is this great attractor really? When astronomers first saw this large-scale drift toward a point in the direction of the constellations Centaurus and Norma, the area was a problem because it lies partially behind the plane of the Milky Way. Dust and gas from our own galaxy block visible light in that zone, creating what used to be called the zone of avoidance. But radio and X-ray observations can see through a lot of that. When we look with those tools, we find dense clusters and groups of galaxies in that direction. Big piles of mass that help explain part of the pull. Further out along roughly the same line is something even larger, the Shapley concentration, a huge collection of galaxy clusters, one of the biggest mass concentrations nearby on these scales. In your mind's eye fly-through, you can picture streams of galaxy motions, little arrows on thousands of galaxies, all slightly bent toward these massive knots. The Great Attractor isn't a single object like a black hole, it's a name for a region of enhanced gravity, built from many clusters and a lot of dark matter. So where does that leave your address, if everything in this region is sliding downhill together? For a long time, where we live stopped at smaller scales. First, we just said we live in the Milky Way. Then we realized the Milky Way is one member of the local group, then that the local group is part of the Virgo Supercluster, a larger overdense region. Laniakea pushes that further. It groups together many clusters and groups, including Virgo and us, based on which way their galaxies are flowing. If their motions, after removing cosmic expansion, point them toward the same overall basin, they are part of the same supercluster. In that sense, we live not just in a galaxy, not just in a cluster, but in a giant gravitational drainage basin called Laniakea. This is a different way of thinking about location. Your upstream and downstream are defined by gravity, not by some arbitrary line on a map. And it gets more radical, because once you start thinking in terms of flows instead of fixed positions, the universe stops looking like a static 3D model and starts looking like a velocity field. When scientists map these galaxy flows over large volumes, they are effectively turning space into something like a fluid simulation. Every galaxy is a tracer particle. Each arrow is its peculiar velocity, pointing toward local overdensities away from underdense voids. Put all of them together, and you see massive regions feeding into bigger nodes, forming a network of cosmic currents. Some areas are slowly draining toward the Great Attractor region, others toward Shapley, others toward different clusters still farther out. This flow field view reveals hidden mass structures too. If galaxies are all accelerating slightly toward an area where you don't see much visible matter, that's a hint that there is a lot of dark matter there. It's another way gravity exposes what light misses. So space is not just a static backdrop where galaxies sit like pins on a board. On these scales, it's more like a moving landscape with hills and valleys in the gravitational potential and galaxies drifting along the slopes. Now put yourself back in it. You're crossing hundreds of millions of light years in minutes, blowing past galaxy groups, clusters, and superclusters that are all part of a larger flow pattern. At this speed, even Laniakea starts to look small, but zoom out just a bit more, and something even stranger appears. The flows you've been following aren't random, they trace out long filaments, sheets, and huge empty voids, a structure so large that individual clusters shrink to tiny knots on threads. So the obvious next question is, if your home supercluster is just one basin in a much bigger pattern, what does the entire large-scale structure of the universe look like when you crank your view out to hundreds of millions of light years per second and start seeing the full cosmic web? What do you call it when far away stops meaning anything, and whole galaxy clusters shrink to dots on lines? At your current speed, 1 second is now enough to jump the entire distance between massive clusters. You're not thinking in millions of light years anymore, you're thinking in hundreds of millions. This is the scale where the universe finally shows its full skeleton, the cosmic web. As you zoom out, the picture changes completely. Individual galaxies disappear into specks, galaxy groups blur, clusters become single points. When astronomers built huge redshift surveys like the Sloan Digital Sky Survey and others, they didn't just see a random sprinkle. Plot tens or hundreds of thousands of galaxies in 3D, and a pattern pops out. Long strands, big junctions, giant empty regions. It looks like a web with filaments, nodes, and vast voids. So here's the key question. If gravity pulls everything together, why didn't the universe just collapse into one big lump instead of this foam-like structure? The answer is in how structure grew from the early universe. Right after the Big Bang, matter wasn't perfectly smooth. There were tiny variations in density. Slightly denser spots pulled in more material, slightly emptier spots lost out. Over billions of years, under gravity and with dark matter doing most of the pulling, those small bumps grew into the structures you're flying through now. The cosmic web is what you get when you let those tiny early ripples evolve for a long time in an expanding universe. As you cross this web at 1 light year per second, you're mostly riding along the filaments, the highways of galaxies. Clusters don't float alone, they sit at the intersections of these filaments. Each filament is a strand of enhanced density, stretching for hundreds of millions of light years. Along them, you get a chain of clusters, groups, and galaxies, all linked by shared dark matter and gas. In between the big nodes, there are smaller knots and branching paths, but the overall impression is clear matter prefers to live on these strands. Simulations of structure formation, where you start with a nearly smooth distribution plus tiny early universe fluctuations, then let gravity and dark matter run the show, produce almost the same web. You see filaments, nodes, and voids in the virtual universe that look like the real thing from surveys. That is a huge reality check. It means our basic model, dark matter plus expanding space plus gravity, really does grow the kind of structure we observe. So if filaments are where the matter piles up, what's going on in the giant gaps between them? Those gaps are not just empty drawing space, they are real regions, called voids. They are tens to hundreds of millions of light years across, with very few galaxies inside. When surveys count galaxies, they don't just see a lack of data, they see actual underdense zones where the galaxy number drops dramatically. These are not artifacts, they are part of the structure. In a void, the average density of matter is less than the cosmic average. That has consequences. With less mass to slow expansion locally, The space inside voids can expand slightly faster than average. In studies of galaxy flows, you can see this. Galaxies tend to drift away from voids and toward filaments and nodes. You can think of voids as regions where gravity has effectively evacuated most of the matter toward the surrounding web, leaving behind slightly faster expanding bubbles. That leads to another important question scientists had to ask. If galaxies and clusters are just the bright tips of the web, where is all the normal matter that should exist according to early universe measurements? We know from the cosmic microwave background and from Big Bang nucleosynthesis how much baryonic matter, normal protons and neutrons, the universe should contain. For a long time, when astronomers added up all the normal matter in stars, cold gas and hot gas in clusters, they came up short. A big fraction of the expected baryons were missing. The current picture says a lot of that missing normal matter lives not inside galaxies, but in the web itself, in a phase called the warm-hot intergalactic medium, or WAIM. This is very diffuse gas, hotter than normal intergalactic medium, but cooler than the extreme cluster cores, sitting mostly in filaments. You don't see it glowing brightly, it's too thin, but you can detect it indirectly. When light from a distant quasar or galaxy passes through these filaments, some X-rays and ultraviolet photons get absorbed at very specific wavelengths, leaving faint fingerprints in the spectrum. Stack enough observations, and the signal appears. A sizable chunk of the missing baryons is out here, in the strands you're racing through, not locked inside galaxies, so now your view of the universe has flipped again. Galaxies are not where most of the normal matter is. They're more like dense knots on a much larger, much more diffuse structure. And that brings you to the real paradigm shift. For a long time, it was natural to treat galaxies as the main building blocks of the universe, like islands in an ocean. The cosmic web kills that picture. The basic unit is not an isolated galaxy, it is the pattern of density across enormous scales. Filaments, nodes and voids together make the structure. Galaxies and clusters just trace it. On this scale, the universe is less like a simple sprinkle of lights and more like a three-dimensional foam, with walls and edges where matter collects, and big bubbles where it does not. Dark matter sets up most of the web skeleton. Normal matter flows along that shape, cools, and forms stars in the densest spots. The cosmic web is the result of gravity working for billions of years on tiny initial differences. For you, this all compresses into a few dramatic moments. Each second you cross distances that would normally take galaxy clusters billions of years to drift across. Filaments streak past, nodes flash by as rich clusters, voids appear as stretches where your galaxy counter barely moves. Underneath all of it, the same ingredients keep showing up. Dark matter shaping the framework, normal matter filling in, and gravity plus expansion competing to control the future. And now that you've seen the present-day web, another question is sitting there, waiting. If today's universe looks like that, what happens when you turn your camera around, stop rushing through space, and instead look straight back in time, using deep observations to see galaxies as they were billions of years ago, catching the web while it was still forming? How do you look over there and actually see back then, not in a poetic sense, in a literal physics sense? At the scales you're at now, hundreds of millions of light years per second, talking about kilometers is pointless. The useful number is redshift. We call it Z. It tells you how much the light has been stretched by the expansion of the universe, and that stretch tells you how far back in time you're looking. So for a moment you slam the brakes on your impossible 1 light year per second flight, you stop flying through space, and instead you point your camera at one tiny spot in the sky. A patch so small it's like the area covered by a grain of sand held at arm's length. You stare at that spot for a long time with a powerful telescope stacking more and more exposure. That's what the Hubble Deep Field did. And when you finally look at the result, that empty patch extends into thousands of galaxies layered by distance and time. Here's the key point. Every one of those galaxies is not just far away, it's old light. The farther it is, the longer its light has been travelling, and the more the expansion of the universe has stretched its wavelength, pushing it from blue to red, then into infrared. That stretch factor is what we call the redshift, Z. Small z means nearby and recent, big Z means far and ancient. So what does that really buy you? It buys you a direct look into the past. Take a galaxy at a redshift of around 6. That means the wavelength of its light has been stretched by a factor of about 7 compared to when it was emitted. When you plug that into our best cosmological model, with a specific expansion rate today, a measured matter density, and a dark energy density, you don't just get far, you get a look-back time. For Z at around 6, you are seeing that galaxy as it was less than 1 billion years after the Big Bang. The light has been on the road for more than 12 billion years before it hits your telescope. You don't need your 1 light year per second sheet anymore. The universe has already done the work. The farther you fly in redshift, the earlier the slice of time you're seeing. Distance, expansion, and time are linked through that model, so redshift turns into a clock. So then you ask, do galaxies actually look different back then? Or are we just seeing the same kinds of things farther away? Deep surveys say they really are different. When you look at high redshift galaxies early in the universe, they tend to be smaller, clumpier, and more irregular. They don't have neat grand design spiral shapes yet. They are full of gas, and many of them are pumping out new stars at furious rates. As you come forward in time to moderate redshifts, you see a pattern in the universe as a whole. If you add up how many stars are being formed per unit volume of space at different epochs, you get a curve. That star formation rate density rises, peaks around a redshift of about 2 when the universe was roughly 3 billion years old, a phase people call cosmic noon, and then declines to today. That curve doesn't come from one telescope pointing once. It comes from combining many surveys across ultraviolet, visible, and infrared light, counting star formation in galaxies at many distances, and building up a global history. The end result is simple but serious. The universe was more actively forming stars in the past than it is now. We're living in the quiet after the busiest era. Now bring in the new player that turned this from impressive to slightly alarming, the James Webb Space Telescope. JWST looks in infrared, exactly where the light from very high redshift galaxies gets shifted. When it started doing deep observations, it found something surprising. Some very early galaxies, at redshifts of 10 and above, appeared brighter and more massive than many models had predicted for such early times. In plain language, it looked like there were big, well-built galaxies already in place a few 100 million years after the Big Bang, when we expected things to be more baby-sized and chaotic. That doesn't mean the whole cosmological model breaks. The basic framework, with dark matter, dark energy, and the expansion history we use, still fits a huge amount of data. But these early heavy hitters do push on the details of how quickly gas can cool, fall into halos, form stars, and build up structure. They force people to update simulations, rethink assumptions about star formation efficiency, feedback, and maybe even the first generations of stars. You're watching a field adjust its story in real time because the universe handed back slightly different numbers than expected. So what's the big mental shift from these deep fields? Remember, Hubble aimed at a region that, to the naked eye and even to earlier telescopes, looked basically empty. No bright stars, no obvious galaxies, just a dark patch. When you integrate enough light over enough time, that patch turns into a crowded city of galaxies stacked all the way back toward the early universe. That single result smashed the idea that most of the sky is just nothing. In terms of structure, every direction is loaded. The only reason most of it looks blank to you is that your eyes are weak and you don't stare for days at one spot. So now you can combine two things. The cosmic web shows that matter is arranged in a huge network of filaments and nodes. The deep fields show that every tiny pencil beam you choose through that web is lined with galaxies at many distances, all the way back to early times. There is no special direction that has the stuff, and another that doesn't. Large scale, the universe is filled with structure in every direction you care to look, as far as the light can take you. And that raises a harder question, one you can't dodge. You've seen mature galaxies, you've seen the peak of star formation, you've seen surprisingly big systems very early on. But there has to be a point before galaxies, before most stars, when the universe was dark, filled with neutral hydrogen and invisible dark matter, waiting for the first light sources to switch on and start changing everything. So what did the cosmos look like before the first galaxies in your deep field, before cosmic noon, before even that first billion years, when the first stars and black holes formed and began to tear apart the dark neutral fog? What does the universe look like when it has matter, gravity and space, but no stars at all? No galaxies, no planets, just a dark cooling fog. That's the state you're flying back into now, past the deep fields, past the first visible galaxies, into the era called cosmic dawn. Right after the universe formed, it was a hot plasma, a mix of free electrons, protons and photons all bouncing off each other. Then, a few 100,000 years after the Big Bang, it cooled enough for electrons and protons to combine into neutral hydrogen. That moment is called recombination. Once that happened, light could finally travel freely, and that ancient glow is what you see today as the cosmic microwave background. But after recombination, something strange happens, nothing obvious, no stars yet. The universe enters the dark ages. You have neutral hydrogen gas everywhere and dark matter everywhere, but no bright sources. Tiny density bumps seen in the microwave background. Slightly denser patches and slightly emptier patches start to grow under gravity. Over hundreds of millions of years, dark matter clumps pull in more material, building the first dark halos, and the gas follows them in. Slowly, those halos become deep enough that gas can cool, condense, and finally reach the conditions needed to form the first stars. So the obvious question is, what were those first stars actually like if there were no heavy elements yet? Those first stars are called population 3 stars, and they're basically ghosts to us right now. We haven't seen one directly, but we can still say quite a lot. Because the gas back then had almost no elements heavier than helium, its cooling behaviour was different. Simulations and physics of gas cooling say that under those conditions, the clouds tend to fragment into bigger chunks, leading to stars that are much more massive than the average stars forming today, tens to maybe hundreds of times the mass of the Sun. Massive stars like that burn fast. They run through their nuclear fuel in just a few million years or less, then explode as supernovae or collapse into black holes. Those explosions throw out the first heavy elements, things like carbon, oxygen, silicon, iron, into the surrounding gas. Later generations of stars, the ones we can see now, carry chemical fingerprints of that early enrichment. When astronomers study the most ancient metal-poor stars in our galaxy, or measure the overall abundances of elements in the universe, they get constraints that point back to an early generation of massive metal-free stars that lived fast and died young. So if the first stars are gone, and we're inferring them from chemical leftovers and simulations, can we ever see the time before them directly? That's where 21 centimeter cosmology comes in. Neutral hydrogen atoms can flip the orientation of their electron spin relative to the proton spin. When they do, they emit or absorb a photon at a very specific radio wavelength, about 21 centimeters. In the dark ages, before stars turned on, and during the early phases of cosmic dawn, the universe was full of neutral hydrogen that could emit or absorb this line. Because of cosmic expansion, that 21 centimeter line gets stretched to longer wavelengths, into the meter range and beyond, by the time it reaches us. Experiments like LOFAR, HERA, and others are trying to detect this faint background as a function of redshift. In practice, that means building huge radio arrays, dealing with a ton of foreground noise from our own galaxy, and trying to extract a very weak, fluctuating signal. If we manage to map that 21 centimeter signal over time, we'll essentially get a movie of the Dark Ages and cosmic dawn. We'll see when the first stars and galaxies turned on, how they heated and disturbed the hydrogen around them, and how the initially smooth fog broke up into bubbles of ionized gas. That leads to the next major transition, which is not just about light turning on, but about the entire state of the intergalactic medium changing. Once enough early galaxies, and especially early quasars, started producing strong ultraviolet light, that radiation began to hit the neutral hydrogen in the space between galaxies. Those UV photons had enough energy to rip electrons off hydrogen atoms, ionizing them. At first, each galaxy created its own bubble of ionized gas, carved into the neutral background. As time went on, these bubbles grew and merged, until most of the hydrogen in the intergalactic medium was ionized again. This process is called reionization, and it's not just theory. We see its imprint in quasar spectra. When we look at very distant quasars, their light passes through a lot of intergalactic hydrogen on the way to us. Neutral hydrogen absorbs specific wavelengths, leaving a forest of absorption lines. At very high redshifts, around 6 and above, those spectra show regions where almost all the light below a certain wavelength is absorbed, a Gunn-Peterson trough. That tells us there was still a lot of neutral hydrogen around. Below that redshift, the troughs mostly vanish, meaning the hydrogen between galaxies was largely ionized. From this, we infer that reionization was mostly finished by a redshift of around 6. So the universe didn't just gently brighten, it went through a phase transition, a global change in the state of its gas. And here's the bigger, slightly unsettling pattern. The universe's transparency has not been a constant boring property. It changed dramatically twice. First, in the early plasma phase, light was trapped, scattered constantly by free electrons. Then recombination happened, atoms formed, and the universe became transparent for the first time. That gave us the cosmic microwave background. After that, during the Dark Ages, the universe was transparent in principle, but it was dark. No bright sources, just neutral gas and background radiation. Then, as the first stars and galaxies formed, they flooded the universe with high-energy light, and reionization began. The intergalactic medium switched from mostly neutral gas to mostly ionized plasma again, but this time the photons came from structures, not from the overall temperature of the universe. Space went from plasma to neutral gas to ionized fog driven by the growth of structure itself. So space is not a passive stage where things just happen on top. It reacts, it changes phase, it remembers. The state of the gas, the temperature, the ionization, all feed back into how easily light can travel, how fast structures can grow, and what you can see when you look back. And that sets up a serious next step. You've gone from the cosmic web of today, back through the build-up of galaxies, into the first stars and the reionization of the universe. But there's a harder wall behind that. Before the first stars, before even the neutral gas, is the surface where the oldest light we can ever see was released. The cosmic microwave background itself, a snapshot of the universe when it was just a few 100,000 years old. So what happens when you keep going back right up against that wall and start reading the tiny temperature ripples on that ancient light to pull out the basic numbers that describe the whole universe? What happens when you keep looking back in time and you finally hit the oldest light you can ever see? A literal wall of information. That's where you are now. You've flown past galaxies, past the first stars, past the reionization era. Go back about 13.8 billion years to when the universe was only around 380,000 years old, and you slam into the cosmic microwave background, the CMB. This light is not sitting behind all the galaxies in one direction. It's a three-dimensional shell around you, like the inside of a sphere. Every direction you look, if you could see microwaves with your eyes, you'd see this glow. What you're actually seeing is the moment when the universe cooled enough for free electrons and protons to combine into neutral hydrogen. Before that, photons were constantly bouncing off the electrons trapped in a hot plasma. After that combination, the photons were suddenly free to travel. The CMB is that released light, stretched by expansion from white-hot to microwave. So what does this ancient glow actually look like when you measure it carefully? Satellites like COBE, WMAP and Planck were built to do exactly that. They looked at the microwave sky and measured both its overall spectrum and its tiny variations. The overall spectrum is extremely close to a perfect blackbody, the kind of spectrum you get from an ideal thermal source, with a temperature today of about 2.725 degrees above absolute zero. That alone tells you this is relic radiation from a hot early phase that has been cooled and stretched by expansion. But the really important part is not the smooth background, it's the tiny bumps on top. The temperature is not exactly the same in every direction. It varies by about 1 part in 100,000. Those are tiny ripples, but they are real, and they are not little noise. They encode information about the density variations in the early universe, the seeds of all later structure. So the obvious question is, how do you turn those tiny temperature spots into hard numbers about the whole universe? You don't just look at the map and say that looks bumpy. You take those variations and analyze them statistically. One key tool is the power spectrum, which basically tells you how strong the fluctuations are on different angular scales on the sky. When you do that for the CMB, you don't get a random curve. You get a series of peaks and troughs at specific scales. Those peaks are not cosmetic. They are the frozen imprint of sound waves, pressure oscillations in the hot plasma before recombination. Back then, gravity tried to pull matter into denser regions, while radiation pressure pushed back. That tug of war created oscillations, compressions, and rarefactions like sound waves in a fluid. At recombination, when the photons decoupled and the plasma turned into neutral gas, those oscillations were effectively frozen into the density and temperature pattern. The first peak, second peak, third peak, and so on in the CMB power spectrum are directly linked to those modes. Now here's the punchline. The positions and heights of those peaks depend on the basic parameters of the universe. Change the total matter density, those peaks shift and change shape. Change the amount of normal matter versus dark matter, you alter the relative heights. Change the overall geometry, whether space is flat, open or closed, you shift the angular scale of the peaks. By fitting the observed CMB power spectrum, we can pin down things like the curvature of space, very close to flat, the density of baryons, the density of dark matter, and the fraction of the total energy that acts like dark energy. But temperature alone isn't the end of the story. The CMB light is also polarized, and that adds another layer of tests. When photons scatter off electrons, they can pick up a preferred direction, polarization, depending on the pattern of the radiation field around them. The CMB polarization map carries extra information about the velocity and density fields at recombination. When you separate the polarization into different patterns, you can compare those to what you expect from standard physics in an expanding universe. On top of that, the CMB photons don't travel through an empty, flat nothing on their way to you. They cross billions of years of evolving structure. As they pass by galaxies, clusters, and dark matter clumps, their paths get deflected slightly by gravitational lensing. That lensing subtly distorts both the temperature and polarization patterns on the sky. By measuring those distortions, you get an independent handle on how much structure has grown over time. That, in turn, lets you constrain things like the total mass of neutrinos, because massive neutrinos affect how fast structures grow. All of this means the CMB is not just some pretty coloured map. It's a precision dataset where tiny details matter. The error bars are small. That's why people say the CMB turned cosmology from a playground of ideas into a precision science. You can't just toss in a new theory because it sounds nice. It has to reproduce that black body spectrum, those temperature fluctuations, the acoustic peaks, the polarization pattern, the lensing signal, all at once with the right numbers. For you, as you conceptually hit the CMB, this is the end of direct vision. Beyond this scattering surface, the universe was opaque to light. You can't see earlier times with ordinary photons, they were trapped in the plasma. You're looking at a hard wall, the earlier snapshot of the cosmos in light. And that raises the next, even more uncomfortable question. If this is as far back as light can show you, how do you explain why different parts of this shell look so similar in temperature? when they should never have had time to talk to each other? Why is the geometry so close to flat when many initial conditions would curve it strongly? Those problems forced cosmologists to reach for a more radical idea, something that happened before this oldest light, an extremely rapid early expansion called inflation. How do you explain a universe that looks too smooth and too flat without just saying, that's how it is, deal with it? You've hit the wall of the cosmic microwave background now, and that's exactly where two big problems show up: horizon and flatness. Start with the horizon problem. When you look at the CMB in opposite directions on the sky, those patches are so far apart that in standard Big Bang expansion, without anything extra, they could never have exchanged light or heat before the CMB was released. There wasn't enough time for signals to cross between them. They were out of causal contact. But their temperatures matched to about 1 part in 100,000. That means they somehow ended up in almost perfect thermal equilibrium, like they had torqued and settled on the same temperature. Standard expansion can't do that in the time available. That's a real physics problem, not just I don't like coincidences. Then the flatness problem. When we measure the curvature of the universe using the CMB and other data, space comes out very close to flat geometrically. Not strongly positively curved, not strongly negatively curved. Flat within a few percent or better. But in the basic equations, curvature doesn't stay tame on its own. If it starts slightly different from flat, it tends to grow over time. To get the universe as flat as we see it today, you'd have to fine-tune the initial conditions to an absurd degree. Again, not impossible, just extremely suspicious if you care about cause and effect. So the question is, do you accept those as just lucky starting conditions, or do you look for a mechanism that forces the universe toward uniform and flat? That's where inflation comes in. Inflation is the idea that very early on, a tiny fraction of a second after the Big Bang, the universe went through a brief period of exponential expansion. Space didn't just expand, it doubled in size, again and again in an extremely short time. This is driven in the models by some high-energy field whose energy density acts like a kind of temporary super strong dark energy. If you have even a small region that's roughly uniform and roughly flat and you blow it up by an enormous factor, that patch will look extremely uniform and extremely flat afterward. Curvature gets stretched away like smoothing wrinkles in a balloon by inflating it. Regions that were once close enough to share information to come into equilibrium get ripped apart so far that later on they look causally disconnected. From our point of view now, opposite sides of the sky never had time to talk under normal expansion. But inflation says earlier on they were neighbours before getting stretched apart. So inflation is not just a wild fix. It directly tackles horizon and flatness with a specific physical process, rapid early expansion. But you shouldn't accept a new piece of physics just because it solves two headaches. It has to make testable predictions. Inflation does, and this is where things get really weird in a good way. During inflation, quantum mechanics still applies. Fields fluctuate on tiny scales constantly. Usually those tiny quantum jitters average out and stay microscopic. But if space is expanding exponentially, those fluctuations can get stretched to macroscopic, even cosmic sizes. The picture is, small quantum ripples in the inflation field get blown up, frozen in as slight overdensities and underdensities in the energy density of the universe. When inflation ends and normal expansion takes over, those imprinted density variations are still there. They're tiny, but gravity starts to amplify them. Over billions of years, those small seeds grow into the large-scale structure we see today. Galaxies, clusters, filaments. In between, they also show up as the temperature and density fluctuations in the CMB, so you get this insane link. Quantum fluctuations on subatomic scales in the very early universe become the seeds of galaxy clustering on hundreds of millions of light-year scales. Quantum fuzz to cosmic structure. That is one of the wildest but also most strongly supported chains of reasoning in modern physics. Now, different inflation models, different shapes of that early field and different dynamics, don't all give the same pattern of fluctuations. They predict different detailed forms of the primordial power spectrum, how strong the initial fluctuations are at different scales. A key number here is the spectral index, which tells you whether fluctuations are exactly the same strength on all scales, or slightly more on some scales than others. Observations of the CMB power spectrum show that the spectral index is close to, but not exactly, scale invariant. It's around 0.96 instead of 1. That slight tilt matches what many inflationary models expect, and it rules out a lot of naive versions. On top of that, inflation can generate gravitational waves, ripples in space-time, which would leave a particular pattern in the polarization of the CMB called B-modes. We haven't seen a clear primordial B-mode signal yet, only upper limits, but those limits are already cutting down the space of allowed models. In other words, we're using sky data to kill bad inflation ideas. The models that survive have to line up with the observed spectral index, the overall fluctuation amplitude, the absence as far of strong primordial gravitational wave signatures, and many other constraints. Inflation is not a free-for-all anymore, it's tightly squeezed by data. So where does that leave inflation as an idea? Is it proven? No, not in the same way that the Earth orbits the Sun is proven. Inflation is a framework that fits a lot of observations very well, but we don't have a single, fully nailed down, agreed upon version of it. We don't know exactly what field drove it, or what the underlying high-energy physics really is. It's also possible that some other, as yet uninvented mechanism could reproduce the same observational successes. But here's the important part. Inflation is not just a patch stuck on a broken model. It makes multiple independent predictions that have been broadly confirmed. It connects CMB data, large-scale structure, and the basic parameters of the universe into one story. That's why many cosmologists take it seriously, even while they poke it and try to break it. This part of cosmology is still active and messy. New CMB experiments, new galaxy surveys, and future probes will keep tightening the screws. For you, as you conceptually rewind the universe past the CMB, inflation is the best current explanation for why the oldest light looks the way it does, and why the large-scale universe looks so uniform and flat, while still having the exact right amount of lumpiness for galaxies to form. And that brings you to the last brutal edge of this entire flight. Even if inflation happened, even if we map the CMB perfectly and chart the cosmic web in detail, there are limits we cannot cross, horizons we cannot see beyond, information we can never get, regions of the universe forever cut off from us by expansion itself. So the final question is, at 1 light year per second after crossing all these scales and eras, what are the hard limits on what you can ever know about the universe, no matter how good your instruments get, and how does that change the way you think about everything in the first place? How big is everything if there are parts of the universe you can never see, not because they're far away right now, but because the laws of physics will never let their light reach you, no matter how long you wait? This is the last step of your trip. You've flown in your mind at 1 light year per second across cosmic structure and cosmic history. Now you hit something you cannot cross with speed, only with logic. The limits of what you can ever know is draw a hard line between two ideas, the observable universe and the whole universe. The observable universe is the region of space from which light has had time to reach us since the Big Bang, given the actual expansion history. Right now, that radius is about 46 billion light-years, not 13.8. That sounds wrong at first because the universe is about 13.8 billion years old, so you might think the radius should be 13.8 billion light-years, full stop. But while the light was travelling toward us, space itself stretching. Think of it this way. A photon leaves a distant galaxy when the universe is young and smaller. It heads our way, and during its whole journey, the scale of space grows. By the time that photon arrives, the current distance to the place it came from is much larger than speed of light times travel time. When you account for that, the now distance to the farthest stuff whose light we can see is around 46 billion light-years. Outside that sphere, there is more universe. Same physics, as far as we can tell, same kinds of structures, but their light has not reached us yet. Given enough time, you'd think more and more of that region would become visible. But that simple picture breaks once you add one more ingredient: dark energy. Here's the next uncomfortable idea. There isn't just one kind of horizon. Our current best model says the expansion of the universe isn't just continuing, it's accelerating. That acceleration is driven by something we call dark energy, which behaves roughly like a constant energy density built into space itself. Because of that, galaxies far enough away are not just receding, their recession speed, due to the expansion of space, will eventually exceed the speed of light relative to us. Not because they're moving through space faster than light, but because the space in between is expanding fast enough. That creates what's called a cosmic event horizon. There's a distance beyond which, even if a galaxy sent out a signal aimed at us today, the expansion would outrun that signal, and it would never reach us. On long timescales, trillions of years, more and more galaxies will cross that line from our point of view. Their light will become redder and dimmer, then effectively vanish from detectability. The observable universe in the practical sense, the stuff we can still receive new information from, will shrink to our local group and whatever merges into it. So even if you crank your imaginary speed to infinite, there are regions of the universe you're cut off from forever, because information from there will never arrive. That's not an engineering problem, it's geometry plus expansion. Now we have to talk about the biggest we don't know in the whole story you've just flown through, the dark energy driving that acceleration. We know it's there from several independent lines of evidence. Distant type Ia supernovae, used as standard candles, look fainter than they would in a decelerating universe, meaning they're farther away than expected. The CMB acoustic peaks and the pattern of baryon acoustic oscillations in galaxy clustering all together say roughly the same thing. About 68 to 70% of the total energy budget of the universe is in some form with negative pressure, causing accelerated expansion. We call that lump sum dark energy. What is it exactly? The most boring option, which actually fits current data pretty well, is a cosmological constant, a fixed energy density of the vacuum, the same everywhere, unchanging in time. You can stick that into Einstein's equations, and the math does what the observations demand. But when you try to connect that to quantum field theory, the naive predictions for vacuum energy are absurdly larger than what we infer from cosmology, so people explore alternatives, slowly changing dark energy fields, modifications of gravity on large scales, new degrees of freedom. None of those are clearly confirmed, so we're stuck in an annoying honest place. We know the effect, accelerated expansion. We can measure its strength, we can plug it into our models and get good fits, but we do not have a consensus, fundamental explanation for what dark energy is. That's why the next generation of surveys and missions exists at all. We're not done, we're trying to corner this thing. Right now and in the near future, telescopes and missions are mapping weak gravitational lensing, the tiny distortion of galaxy shapes by foreground mass across huge areas of sky. They're mapping galaxy clustering in detail, measuring how structures grow over time, and they're collecting big samples of supernovae at many redshifts. The whole point is to test whether dark energy really behaves like a perfect cosmological constant, or whether it changes slowly with time, and to see if gravity itself follows Einstein's rules unchanged on the largest scales, or if it deviates. Put simply, we're deliberately stress testing the model that got you this far. If it breaks, it'll break in the precision of these measurements. And now we're at the final wall, the horizon that doesn't care how fast you fly in your thought experiment. At 1 light year per second, you can mentally traverse the observable universe in less than a human lifetime. You've crossed from planets to the Oort Cloud, from the local bubble to the galactic center, from the Milky Way to the local group to Virgo, to Laniakea, to the cosmic web, to the first stars, to the CMB, and right up to inflation. Speed was never the real limit. The real limits are about information. There are regions of the universe permanently outside your event horizon, whose state you can never measure, There is cosmic variance, the fact that you only get one universe to sample, one CMB ski, one large-scale structure pattern, so some questions will always have built-in statistical uncertainty. There is quantum uncertainty, which says you cannot know certain pairs of properties perfectly at the same time. There is the finite age of the universe, the finite speed of light, and the fact that the early plasma phase blocks any attempt to see back before the CMB with normal photons. Together, those are hard walls, not made of matter, made of missing data. Beyond them, you can build models, you can test those models against what you can see, you can rule out bad ideas, but you cannot replace inference with direct observation. That is not a failure of cosmology. That is what makes cosmology a live subject instead of a finished textbook. The universe gives you just enough information to reconstruct a lot of its story, but not enough to turn it into a solved puzzle. There will always be open edges, things you can only approach with probability, with better data and with better theories. And you, with your 1 light-year per second imaginary speed, have just run straight into those edges. You've seen that everything is bigger than what you can see, that most of the matter doesn't shine, that most of the energy is in a form we don't fully understand, and that even perfect instruments could never show you absolutely all there is. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video, and subscribe to the channel for more such amazing videos.